In this tutorial video, we're going to discuss limits, rates of change, and tangent lines. And remember that a rate of change is a relationship between two changing quantities. Typically speaking, in calculus, we're going to talk mostly about velocity. Velocity is one of the most commonly used concepts in all of calculus. So that's the main rate of change that we're going to take a look at. So, for example, if you're going 80 kilometers an hour, what exactly does that mean? Well, it means that our position changes by 80 kilometers for each single unit change in time. And the two main words here are position and time. That's exactly what velocity is. It's a change in position versus a change in time. And just a key note here, in order to use any formula involving velocity, we have to assume that the velocity is constant. In other words, it doesn't change. So in the example above, if we're talking about a problem and I'm telling you that we're going 80 kilometers an hour, we're going 80 kilometers an hour the entire time. It's not going to change. So we want to be really careful that we understand that. Okay, so let's start talking about velocity. We want to be really careful also that we understand the difference between velocity and speed. Those words are very often interchanged, and we need to be really careful that in mathematics, especially calculus, that we understand exactly what the difference is. So the difference between velocity and speed, velocity, it could be positive or negative, and it usually indicates direction. So for instance, if we have something falling towards Earth, we may have something being positive to indicate that it's getting closer to us, or negative in the case that it's getting farther away from us. But either way, they can represent different things. You just have to pay attention to the context of your problem. In other words, this is a vector. It has direction and magnitude. Speed, on the other hand, is the absolute value of velocity, so it's always a positive value. In other words, it's just a scalar. All it has is magnitude. It's just a value. So something else that's really crucial to understand too is typically when we have a problem that is involving velocity, typically we're interested in what happens at a particular moment in time, which means it's instant, it's instantaneous. What happens at this one particular moment? So that's what instantaneous velocity is, and that's typically what questions are going to be asking you. How fast are you going at 1 hour? How fast are you going at 30 minutes? So those kinds of questions. So we want to make sure that we understand instantaneous velocity as well. So now the next thing that we want to talk about is average velocity. So average velocity is just like an average rate of change of any kind. In particular terms of velocity, we still have to deal with position and time. So since time is always an independent variable, remember that this is still the idea of slope. So change in y over change in x. With velocity, though, the position is going to be our y, so change in position, divided by the change in time. So this is our general formula for average velocity, and it's really great to know this. So just real quickly for an example, let's say we have an automobile that's traveling 200 kilometers over a 4-hour time period. To find the average velocity, all we're going to do is follow our formula, which is change in position, which is 200 divided by the change in time, which is 4 hours. So we do that division and we come up with 50 kilometers per hour. And this is really important too. Anytime that you're talking about a rate of change, again, you always need a ratio of units as well. So that's our average velocity. Keep in mind though that average velocity is a good thing to know, but we're really interested in that instantaneous velocity. So this formula is not really going to help us in that sense unless we can make our change in time very, very small. So For instance, what we would do is we would have to know which two time intervals or time slots that we would be interested in looking for. So notice that T1 and T2 here are two different instances of time. One being at 0.5, let's say it's hours since the previous problem was in hours, and T2 being 0.6. Notice that those values aren't pretty close together, but we could make it closer. So for T2, instead of 0.6, maybe I could have it 0.55. That is, in fact, closer to 0.5, our T1. And this can continue getting as close to 0.5 as possible. And the closest we can get those two values together, the more approximate and instantaneous velocity is going to be. So the problem that we just looked at is over 4 hours. That's an incredibly long period of time. Whereas the problem that we just looked at, or the example, is over a very, very small piece of time. And that's where the difference between average velocity and instantaneous velocity takes place. So what we're going to do is we're going to change the average velocity formula just slightly for a specific time interval. So the closed interval that we see here in purple-ish red, I guess, is T naught. That's how you read a subscript of 0. It's called T naught, but it just means your initial time. So from an initial time to some other given time value, like what we were just talking about. So the formula is going to change just slightly in that we call it delta S. S is our universal variable for position over our change in time. And if we ever want to plug this into a formula, the quick and short way of doing it is to take our formula, which will have an S equals value. We'll have S of T1 minus S of T naught, just like your slope formula, just like average velocity, and that's going to be over T1 minus T naught. So all of this is still a rate of change. It's still a slope, except for this, it's over very specific time intervals. And just real quick, this delta S is also called displacement or net change. So those are two of the vocabulary words that mean the same thing for delta S. So what we're going to do next is we are going to discuss some gravity problems that involve velocity. And we need to first of all understand that gravity has its own very specific rate of change and own formula or equation as well. So the general formula for any object in free fall is the position function S of t. Remember, S is referring to position of t is equal to 4.9 t squared meters. This m is not a variable, that is a unit. So we always measure gravity in terms of meters. So here's our example. We're going to have a stone being released from a state of rest, and it's going to fall to Earth. Estimate the instantaneous velocity at t equals 0.8 seconds. So we are going to pick our t naught and our t1. So our t naught is going to be what we start with, which is 0.8. We get to choose T1. And of course, the closer that you can make it, the better it's going to be. So I'm going to make this to be 0.8000001. That's pretty darn close to 0.8. So what we're going to do to find or to estimate our instantaneous velocity is to plug this into our velocity formula. And just to refresh your memory, to determine instantaneous velocity, it's the change in position over the change in time. And if we have a function, in this case we have the gravity function, we're just going to plug our T1 and T0 values into our formula to get our change in position and then determine the difference in time. So let's go ahead and set this up. So there's our setup, and I'm going to plug our T values into the function. And this is what we're going to get. So I plugged in 0.800001 into our gravity function up here that we just looked at. And I got 3.136 originally. But then I plugged in 0.8 and got the same exact thing. That's why you see me having extra decimal values in here, because if I were to just subtract them without giving more decimal places, I'd get 0, and then this wouldn't work. So anytime that happens, get more decimal places in there, and then you'll be fine. So after this, we're going to have this, and we're going to divide these two numbers and get 7.8. Now, granted, if you can get 3 decimals in there, that's going to be better than anything else, but this estimate did not give me any. And keep in mind, too, that you may not choose the same T1 value as your neighbor or classmate or teacher even, and so your numbers may be slightly different. However, your answers collectively should be very close to the same value. That value that this actually does approach is supposed to be 7.840. So I'm pretty darn close. Now we have to add some units onto this, and gravity is always meters per second. So that's how we're going to deal with gravity problems with our instantaneous velocity. So the big question, how are all these ideas related? Well, the first part is that average velocity converges to instantaneous velocity. And the word converge just means to come together. So the smaller and smaller time intervals that you can take will become instantaneous velocity, the closer and closer that T0 and T1 get to each other. Or that instantaneous velocity is the limit of average velocity as the length of the time interval shrinks to 0. Again, remember, we're trying to get T0 and T1 as close together as possible, so that distance approaches 0. And that's exactly what a limit is. We're trying to get as close to a value as possible. And this is a vocabulary word that may be new, may be old, but this is the key thing that's going to come into play in calculus. So understanding that instantaneous velocity is a limit of average velocity is really important, and it only becomes a limit if you try and get closer and closer and closer to a particular value, in this case when time gets close to 0. So the last thing that we need to discuss is how to look at instantaneous velocity or limits graphically. What in fact does it mean when I'm taking a look at a graph? So for example, we're going to take a look at this particular graph. We have a function on the picture. It's going to model the position of some object. So on the horizontal axis you see t being for time and the vertical axis being s for position. So how do we get our t0 and our t1, and how do we get our y values to put into our average velocity or instantaneous velocity formulas? Well, we first of all have to pick our t1 and t0 values. So there we go. I picked 2 random t values. That's where they are. So I'm going to follow those up to our function. So at t0, that's where my point would be, and at t1, that's about where my point would be. Now notice that you could actually connect those 2 particular points to make your own separate line. This is a very special line called a secant line. So I'm going to go ahead and trace that out for you. There we go. It's a little rough, but that's what it is. So we're going to call this our secant line. And of course your secant line is going to change depending on which t values that you choose. So when we talk about that formula for instantaneous velocity, which I just put it up in the left-hand corner in case you've forgotten, remember that this is specifically the slope of a line. So I couldn't just estimate a line going through my t0 and t1 because there is no line for this function, so I have to create one. That's why these secant lines are so helpful, is because I cannot find those instantaneous or average velocities unless I do. So if you look at the formula that we have, I have my t1 and my t0. Where are my s of t1 and my s of t0 values? Well, that's very simple to do. All you need to do is find your points that you have on your function and your secant line and trace them to the y-axis. So if I do that with my t0 point, I'm going to do this in blue for the y-axis. This is going to be my s of t0 value. And the same thing goes for the t1 value, so I'm going to just trace that across the best that I can. I got to use lines to help me. This is my s of t1. So this is very general. So what we are literally doing is finding the slope of the secant line. So that's great and all. Let's say that t naught and t1 though are like that problem that we looked at that are 4 hours apart and we need this to get closer. Well, what would happen to the slope of the secant line then? If t1 gets closer and closer to t naught, what if this guy moves all the way over here? So I'm going to draw that picture out for you as well. So there's our t1 and s of t1 now. These are our new points. So I'm going to go ahead and trace my new secant line that connects t naught to t1 and see what happens. So I'm going to try to do this as carefully as I can. And I'm already noticing that the slope of this secant line is much shallower than the original. And so what do you think is going to happen if I get even closer? What's going to happen to that secant line? Well, it's going to start becoming the tangent line. And a tangent line only touches a function once and never crosses through it. So I'm going to pick one more point as close to t naught as I can. I probably can't even fit it on my graph, but that's where it is. And it's right above my s of t naught as well, just slightly. So notice that those 2 points, once you get them so close together that they almost look like they're the same point, you're only going to have one point where that secant line is going through, or so it's going to seem. That's a tangent line. So all these secant lines, what happens to them is that if the time interval, this distance, gets closer and closer to 0, your secant line becomes the tangent line. And in words, what this means is as the time interval shrinks to 0, the average velocity approaches the instantaneous velocity. So those 2 points getting closer and closer together, they make 1 point. That's instantaneous. 2 points farther apart, that's average. So this is where our limit information kind of comes from. Especially when you see this word, approaches, that kind of sparks the idea of limit in your mind. So when we approach instantaneous velocity, we're also talking about limits. So to sum it all up, in conclusion, we say that instantaneous velocity is equal to the slope of that one single tangent line to the graph of position as a function of time. And that will conclude this tutorial.